All right, hello everyone. So, welcome to the lecture 2 of Getting Started track. Okay, so today we are covering basically Vulkan ecosystem. So, I would say that today is where things start getting interesting because we are moving beyond what Vulkan is and basically try to understand and explore how the entire system actually works together. All right, so I would say that by the end of today's lecture, you will be having a clear understanding of how your application talks to the GPU. Okay, and more or less, how your application talk to the GPU via Vulkan. All right, so we will also actually try to explore what exactly the role of Vulkan driver, SDK, and we understand some of the tools. All right, and I would say that most importantly, all these things are required to understand how a real application or basically an engine development works. Okay, now I would also say that by the end of this lecture, you would be having a clear understanding. What Vulkan it's all about. Okay, at a higher level. So in today's lecture, we will not jump to into the code itself, but at the same time I would say that it is very important for you from an interview point of view. Okay, so I will actually jump into the APIs. So I will give you basically a very high level programming model overview, and I will basically touch up upon basically some of the APIs that all those basically different phases use. Okay, so you don't need to remember all these things. Okay, so I want you to basically focus on building the intuitions and just understand how it works. So now without any delay, let's start with the topics that we will cover. So let's look at what exactly we are going to cover today, and why exactly every part of it matters. Okay, so the very first thing is actually we will start with the Vulkan ecosystem. Okay, so this is where you will start basically understand the team behind the Vulkan. So basically the team comprises of your application loader, driver, the validation layers, and the GPU itself. So all we actually cover it here. Okay, then we will move into basically the next topic, which is understanding the programming workflow. In other words, we will understand the programming model of Vulkan. Okay, so I would say that this is basically the heart of today's lecture. So you will see how everything connects basically. So we start with creating the Vulkan instance to basically finally how the rendering of the frame on your display works. Okay, so finally we will reach to the very last topic, where actually we will understand why Vulkan matters for your applications and game development. So we will look at the roadmap. I would say that this is very important. Okay, so this is important just not from the academic basically perspective, but you are basically using modern graphics, this modern graphics API into real application games engines. Okay, and you are basically building a number of high performance application systems. Okay, whether it is for AI, ML, okay, applications, or any other sort of things. Okay, so this will allow you to directly control the basically GPU, whether it's basically direct control of the memory GPU execution, or basically tuning the performance. So I would say that today's lecture it's very important. Okay, it will help you to understand the overall system workflow, and basically how basically you think as a developer if you are using basically a modern uh, graphics and compute API. Okay, so how can you program it now? So I would say, before we even think about writing code in Vulkan. Okay, I want you to basically take a pause and basically understand something which is very important. Okay, so one thing that you need to understand that Vulkan is just not another graphics API like OpenGL. Okay, it's an entire ecosystem. Once you install basically the Vulkan SDK, okay, you would see that there are basically a number of tools. Okay, we will not jump into all the tools today, so we will look at those tools over the journey. But what you will see is basically it's coming up with an entire ecosystem, and it's very important from a developer perspective, a junior developer or a student perspective, to understand these and and having basically a better understanding what their roles are. Okay, how do you use them? Don't think about this time, but you should be having basically all the nut and bolts. Basically I've been known of the Vulkan, so that you can better understand it. Okay, now I would say that it's by understanding this ecosystem, it makes your application development not only easy, but it fixes a main problem of your application, which is basically debugging. So debugging becomes very easy for you. If you have error, if you have GPU specific errors, you would be able to understand it. Okay, where exactly the problem it's coming from, which stage it's coming from. Okay, also this is important for you for the performance optimization. So most of the companies, they do have their engines. What they want basically new people to come and implement new features and optimize their performance. So performance is something which is never ending. Okay, so you keep hunting for that. All right. Okay, so I would say that by today's lecture, which is basically the Vulkan ecosystem, by the end of this lecture, you would having basically a better understanding who sits where, who controls what, and how's the entire data actually flows. Okay, all right. So I think this is important. Okay, this is basically a Vulkan ecosystem component architecture. So this is the component architecture. All right, now this architecture diagram shows basically a layer design of Vulkan. The key insight is here that the loader is what makes Vulkan very much portable. Okay, so the very first block that actually you will actually see is basically the Vulkan loader. The Vulkan loader is basically, it is an interface between your application and the low level driver. So if you want your application to use Vulkan, okay, you have to go through the Vulkan loader. Okay, so what Vulkan driver it does, the Vulkan loader it does, it basically it's abstract away platform differences. Okay, and basically help to provide utilities like validation layers. Okay, so the validation layers are basically debugging capabilities that are basically injected at the loader level. Okay, so that means if you look this application from top to bottom. Okay, now let's break it step by step. At top, what you can see is that you have basically your basic application, and it contains basically some of your Vulkan code. Okay, this could be basically your engine code, your logic, or any simple code that you just wanted to do hello world. Okay, but one thing that you need to understand, that this application does not talk to the driver directly. Okay, it always talk to basic your driver. Okay, which is the GPU hardware, sorry, through an interface, and that interface we called it as basically the Vulkan loader. Okay, so your application does not directly talk to the GPU. Instead, it goes through something that we called it as Vulkan loader. So Vulkan loader is basically an interface between your application and the GPU hardware. Okay, now the responsibilities of the Vulkan loader is basically to find correct GPU driver. Okay, then loading functions. So the functions, they are basically load in terms of function pointers. Okay, the basic implementation of Vulkan, it's all implemented in C. Okay, so Vulkan is implemented in C language. Okay, so you would find lot of structure, descriptors, functions. Okay, the functions are exports by function pointers. Okay, so this is how the driver is wrote. So we will also see Vulkan CPP, which is basically a CPP wrapper built on top of Vulkan API. Okay, later. But okay, so I was actually discussing the role of in Vulkan loader. So basically, it helps to find your drivers. Okay, load the function pointers. That means it is basically help you to point out all the functions which are available. It also helps you to manage extensions and validation layers. Okay, so injecting layers means you have a lot of debugging and validation layers available with you. Okay, what layer that you are interested in, you will be basically specifying that in your to your Vulkan loader. Okay, through Vulkan instance. Okay, so what it does is basically whatever the layers that you are interested in, it basically injects those layers during the Vulkan load. Okay, loader. Now the next part that comes is basically the driver. So this is 0, this is 1, this is 2. Okay, now the GPU driver, I would say that this part is basically very much vendor specific. So it could be Nvidia, it could be AMD, or basically it could be Intel as well. Okay, so you have integrated graphics card. So I would say that this is uh, this is a layer where your Vulkan commands get actually transferred into hardware instructions. Okay, so the last part is basically is your basically a GPU hardware. But before that one, I think I forgot this one. Okay, so this is where your Vulkan instructions, they get actually change into your hardware instructions. But at the same time, during the development, we make use of validation layers. Okay, so the validation layers are extremely important. So basically they help you to catch mistakes. So if you are doing basically any mistakes in your code, okay, you are not following basically the convention, or basically passing wrong arguments. Okay, it tries to validate it. Okay, it tries to validate and basically show those validation layers in the command line. So we will look at those. Okay, we will cover in the very next lecture. So I would say that the very first thing that you should always do when you create any application code, the very first one is basically you make it modular. That means your engine code should be very much separate from your game code or application logic code. The second thing that you should be doing in the very beginning is bring debugging capabilities as soon as possible. Okay, and full-fledged debugging capabilities, not just basically simple error messages. Okay, so this is where actually you systematically build your application in a scalable way. Now finally at the bottom you have basically your GPU driver. Okay, sorry, the GPU hardware, where the real execution of your Vulkan commands, it happens. All right, now now once you have basically understand basically the architecture, let's talk about your toolkit. Now I would say that without tools, Vulkan is very difficult to work with. Okay, so Vulkans basically comes with Lunar G Vulkan SDK. So it's, did I wrote it? I didn't wrote it. So it's called, so it's called Lunar, ah, LUNAR, Lunar G Vulkan SDK. All right. So so your Lunar Vulkan SDK is your primary development environment. So it gives you everything. It gives you basically the headers that you can see on your screen. Okay, it gives you basically the headers. Okay, and then it will also actually provide you the runtime libraries for Vulkan. Okay, it actually provide you the Vulkan validation layers. Okay, apart from that, it also gives you a number of variety of tools. Okay, so these are just only few tools actually that I'm mentioning. Okay, so we don't need to get into this one, but when you actually look at these slides, you can see, I mean, what exactly each tool does. In the last lecture, actually, I help you to understand the shaders are not directly compiled by the Vulkan itself, but we will actually use some CLI tool, okay, that we called it as GS lang validator. So what it does, it's basically it changes your shader to a binary representation that we called as a .spv. Okay, now .spv you can actually cross compile into basically any language. So that means if you wrote your GL shader, okay, GLSL shader, okay, your shader into GLSL, you can convert into SPV, and then you can basically also use this SPV to compile it into a DirectX shader or basically a metal shader or any other format. Okay, so all these are basically a part of your ecosystem. Now when we actually cover the lectures, I mean, we will look at these in detail. All right, now today is basically a high level overview, so I will just help you to understand, I mean, how everything actually works. Now I would say that, I mean, with this slide, I mean, this is where the slide, I mean, things starts get it really interesting. I mean, unlike OpenGL, so Vulkan does not accept the shader source code, right? So we basically instead use SPIRV, okay, which is basically a binary a binary intermediate representation of your shading language. Okay, so we will give it to GSlang button, and it basically creates a .sp file. So what happens here is basically, so you write your shaders in any shading language. It could be basically GLSL, or it could be a direct X shader language like HLSL. Okay, then you build, I mean, then at the build time you compile these into SPIRV, and it generates basically a .spv, and at runtime the Vulkan wrote this binary and basically creates a shader module. Okay, so I think the shader module, yeah, this is the VK shader module. Okay, from an interview point of view, so you may not require to remember every API, but there are some basically keywords that you should be always, I mean, it should be always on your tips. Okay, so for example, VK shader module, so what it does basically, it uses the .spv and it creates basically a shader module. Okay, then this shader module is basically fed into the VK pipeline, which is basically the graphics pipeline, compute pipeline, or any other pipeline. So what it does, it basically it bakes your shaders and basically uh, create the pipeline. I mean, based on various pipeline states that we will see later. All right. Now, the next thing that actually surprises many students is what that Vulkan does not creates the window. Okay, so it's a complete graphics and compute API. So it does not create the window. So when I say window, its window is basically it's a surface where you wanted to draw something. All right. So Vulkan does not basically create windows. It's a pure graphics and compute API. So what we will do, we will instead use some uh, utility library for surfaces, or it could be basically glfw, it could be basically qt, it could be directly use of xcb. Okay, if you are working with ubuntu, or it could be io surfaces or metal view directly if you are working um, with mac. All right. Now in our case, actually we will make use of jlfw, where we will actually create a window, and we will provide basically a surface. Okay, a surface where Vulkan it can render into. Okay, now for our program we will make use of cmake as well. So you should be ensuring that everything basically you have set up properly. For cmake, I have actually pointed out to you, if you have not basically very comfortable with cmake, you can actually follow these links. Okay, so these links, it will directly take you to some of the helper example to help you get started with cmake. So if you attended my earlier lectures for CMake, I mean, this is what actually basically the source is coming from. So you can actually understand those. Okay, now this particular part, it's coming from the example itself, so you don't need to remember right now. But what we are actually representing here is that we have basically an import dependency cmake, and for glfw we actually directly import the glfw from the source code, and this is the tag that actually we are using it. All right, so you should be having glfw ready, you should be having cmake. We will use it to create window surfaces and basically build our system. Mm, so let me take you to this. So if you go to this link, you will find basically various tutorials. I mean, you can actually start with the basics. Okay, so you can go to this web page. It actually helps you to create tutorials and help you to understand step by step how to create those examples. One thing which is important, I would say, that you try to understand cmake and basically look at how this repository has made. So you can also see that I have actually created make use of mkdocs to basically create this hosted website. Okay, and it's all basically it's a very easy. Okay, so you are just actually creating markdown files, and this is how you can actually do the uh, documentation. All right, so if you don't learn cmake, I would say that this is the time you should be doing that. All right, so cmake is basically quite an industry standard. There are actually many code generators. Okay, so There are a lot of code generators, but CMake is one of the popular code generators for C++. Okay. All right. So let's move to the next slide. All right. Now this is important. Okay. So let's understand what is Vulkan's execution model. Okay. So the picture that you actually see on your screen, I mean, it's what we called it as Vulkan execution model. Okay. So this shows basically how Vulkan actually work internally. Okay, so this diagram, it's very important, spend some time on it. Okay, so it will give you basically a mental model how basically Vulkan works for you. Now in Vulkan, it does not basically directly execute commands, but what you do is basically you record your commands into the command buffers. Okay, and submit those command buffers into queues, and the queues are basically processed by GPU. So I would say that it is very important, or basically to understand this mental model if you wanted to basically make use of multi-threading, or basically better utilize your CPU. Okay, now this entire basically diagram, it's a very big picture. So maybe I can start help you to understand. Okay, so before we write any single line of code, I think this is something that you should be understanding very carefully. Okay, now uh, I mean, this is a part where actually you will write your code into your application, and your application does not talk to your device directly. Okay, but what it does is basically it talks to your device through command buffers, and those command buffers are recorded. Okay, so we create command buffers from command pools. Okay, so what it does is basically it gives us command buffers, and once we have basically those command buffers, what we do is basically we start recording those command buffers. Okay, so this is basically start, and this is basically end. So you can see I have basically a lot of command buffers. So it could be basically a vk, cmd, draw command, or this could be some other command. So when I specify any vk command draw, it does not execute upfront. What it's doing, it's just getting the instructions and it is recording into a command buffer. Okay, so every time I'll say start and end, it's basically something, a recording is happening, and in this one actually I'm specifying a number of basically commands. Okay, now these commands, they are recorded into one command buffer, or they can be recorded into multiple command buffers. Now this is where I would say that it's basically provides a greater advantage over OpenGL. In OpenGL, we know that those commands or those command buffers, they are recorded internally and they are not scalable. Okay, so you cannot make use of multiple threads. Okay, here you can actually record this command buffer separate from this command. So let's suppose it could be, so this is under my thread 1 and this could be under my thread 2. Okay, so we are recording two command buffers, and each command buffer having basically different commands. So 1 2 3 4 5 6. Okay, so it is basically recorded in two different threads. Okay, or it could be basically one thread itself, like I don't use this command buffer which is command buffer 2. Okay, so once these command buffers, they are basically uh, recorded, then it will basically go to the next stage. Okay, now this is where we called it as we submit the command buffers into queues. Okay, so we have basically various type of queues. Okay, so in this example you can see I have q1, q2, q3. Okay, so you can see that both command buffer 1 and command buffer 2, they are basically sent into q1. Okay, so what exactly the queue is, I will actually help you to understand queue in upcoming slides, but you just try to understand that your device, it exposes a number of queues. These queues basically expose the capabilities of this device. So that means a queue, maybe it's a graphics queue, or maybe it's a compute queue, or maybe it's basically a DMA queue. Okay, direct memory transfer queue. Okay, so what a queue does, it does basically a specialized operation. So graphics queues means it's using the command buffers and it's only drawing. The compute queue, what exactly it's doing, it's basically accepting command buffers and it's doing the general purpose compute problem, number crunching. DMA, if you wanted to transfer any data from your CPU to GPU, these are basically special queues to transfer your, so there is no processing going on. All right, so you have basically various type of queue. So maybe, so this is, I will call G, C and D. Maybe this queue, it's basically very specialized, it is capable of doing G, C and D. However, this queue, it's capable of only doing G and D. Okay, this compute, it's only capable of doing C and D, compute and DMA. All right, so this is how the mental model works for the the execution model works. So once we actually recorded these, recorded the command buffer, we send them into the queue, and the queue, they keep the command buffers into a sequential manner. That means if CB1, it's sent first, it will be executed first on the device, and command buffer 2 later. All right, now this slide shows basically a big picture pipeline. Okay, and I want you to basically remember this. Okay, now here every Vulkan program, you will write this. Okay, this kind of model to basically implement your application. Okay, so I think we will discuss more this in the upcoming slide, so maybe I'll just move to the next slide. All right, now there are basically 6 stages of your Vulkan application. Okay, now we will discuss these stages one by one in detail. Okay, but here is basically the high level simplified overview. The very first thing that actually you will see, that we will do the hardware initialization. We will do the hardware initialization. Okay, and I would say that this is a step where your program, it gets connected with the GPU. Okay, now in each of these stages you can see that I have added basically some of the Vulkan APIs. So you don't need to remember these, but once you actually complete this lecture, once you have basically not this lecture, but once you have basically completed this track, and when you come back to these slides, it will start making more sense. That okay, and the reason actually I added, I mean, it's basically a cheat code for your interview. Okay, so how Vulkan execution model works, how the application workflow works, so this is helpful in that situation. Okay, now the second thing, the stage is basically Windows and swap chains. So what we will do, we will prepare our Vulkan system to render something. So what we will do, we will prepare the display system here. Okay, then the third stage is basically the resource setup. Like I mentioned before, in Vulkan we have only two type of resources, buffer and images. So we will deal here with buffers, we will deal with images, image memory, okay, and we will deal explicitly with the memory management here. Okay, the next step comes is basically the pipeline setup. Okay, so here you would basically specify your shaders and basically do all the rendering configurations for your program. Okay, so in short, you will actually create pipeline state objects here. Okay, the fifth stage is basically where you will start recording the command buffers. So command buffers are basically the actions that you wanted to do. Okay, so all those actions are recorded into the command buffer. So what you will do, basically you will do the command buffer recording, and in the last stage, okay, you saw this part, right? So this is where the command buffer recording is going on. All right, so command buffers, they are created for basically from command pools. Okay, and those command buffers then recorded into a, those commands are basically recorded into a command buffer and given to a particular queue that you are interested in. Okay, and finally what we do is basically we will submit these command buffer into queue and basically present means we will actually display it. So this is basically the overall basically high level overview of this, the Vulkan application overview, application workflow. So let's look at basically the very first stage, which is basically the hardware initialization. So I would say that everything starts here. So the very first job of your application is to create a Vulkan instance. Okay, so Vulkan instance is a way where your application, it can talk to the GPU. And how does it talk? You create basically a Vulkan instance object and you pass basically a number of information into it. Okay, so for example, which what validation layers you are interested in, what extensions you are interested in, all those kind of things you would actually pass here. And once you pass this, it will go to the Vulkan loader and it will try to basically look for those extension functions, load their function pointers and basically provide you the access for those. Apart from that, it also basically inject the debugging layers for you. All right, now once you have actually created a Vulkan instance, the next step for you is basically to access the GPUs. So the very first step what you did is you created a Vulkan instance. Now you are capable of doing basically basically you're capable of now using Vulkan on your in your application. The next thing that you wanted to do is basically you wanted to check for the available devices on your basically system. All right, and this is where we will do basically we make use of this API, okay, which is VK enumerate physical devices. Okay, so what it does is basically it takes the instance and it returns you a number of devices. From those devices, those are basically the physical devices. For example, on my system I do have basically a GeForce RTX card, plus along with that I do have also an integrated Intel graphics card. All right, so that means if I'll make use of this API and I'll query the GPUs, it will provide me 2 GPUs. Then what I can do is basically I can choose one of this GPU, okay, to basically do my stuff. Okay, now whenever I say that I can choose basically one GPU and do my stuff, I'll always do it in the logical device. We never make use of physical device. So physical device is actually the real hardware, but the logical device is basically the interface to it. So we will always make use of interface to it. Okay, So one thing, I mean, I would say that, I mean, if you look at this a high level, I mean, pseudocode. So Vulkan, it's not assuming anything. So you are actually responsible for any actions that you are actually doing. So it's just giving you query capabilities, and once you get those, you have to basically use them accordingly. So there is no guesswork behind. Okay, so everything that you wanted to do, you have to do manually through programming. Okay, so I mean, you don't need to remember all these things, so it's just a high level overview for you to basically understand. Okay, so once we will start everything programming in the next lecture, but it's important for you to understand the flow, how it works. Okay, so this is the hardware initialization. So this is the hardware initialization part. Okay, so you create instance, then you get the physical device. Once you get the physical device, then you create a logical device, which is an interface, and once you get the logical device, then you actually get the queues. Okay, so it can basically return a number of queues. So usually we get basically queues in the form of families. Okay, so what those families are, the families actually represents whether it is capable of doing graphics application operation, compute operation, or direct memory transfer operation. Okay, so these are different type of families. Okay, all right. Now this is, I would say, now we are entering something which is very important. This is where your application actually starts becoming visible on screen. Okay, so up till now, whatever the programming that you have done, okay, it's just talking to the GPU. Okay, you cannot display anything. Okay, whatever you retrieve, you can just, I mean, display it as a text in the command line. Okay, but if you wanted to render something, you need some kind of surface, right? So the very first concept here is basically the surface management. Now think of the surface as basically a bridge between your operating system and your Vulkan. Okay, now the Vulkan itself, like I mentioned, it does not provide any kind of window to you, right? So what it does, it's basically, it provides basically the APIs, and those APIs, it needs to basically draw something. And where exactly it draws? It draws on the surface. Now the surface is basically, the surfaces are managed by the operating system. So the window does not create it, sorry, the Vulkan does not create it. Okay, it does not know anything about the windows. So what it knows, it knows just about the surface. So the surface, it would be created by the operating system. Now you can directly make use of operating system to create those basically windows surfaces. Okay, or you can basically use of a higher level API like glfw qt. Okay, but if you are basically dealing with the lower level, okay, you can directly create those surfaces. So for example, if you are working on Ubuntu, okay, you can directly use xcb basically to create the surfaces. Okay, now there is one important thing that actually you will find. There is an, okay, so I would say, let's look at this code. So this particular part, I mean, what we are doing basically, we are creating a glfw window, and so we are creating basically a glw surface, and we pass basically a glf window pointer into it, or basically an object into it. So what it gives is basically, it gives a vk surface khr. Now anything that starts with khr, okay, it's basically an extension. All right, and it's basically an extension for Windows surface management. Okay, so whenever you see vk surface khr, it really means that this is a place where you are basically uh, your rendered image will appear on the screen, okay, in a layman terms, okay. So the next thing that comes is basically the swap chain, okay. What exactly the swap chain is, okay, these are basically a set or basically a queue of displayable images, okay. Now I would also say this is basically the real heart of rendering. Now if you understand this, I mean, it becomes much more easier to manage the swap chains, okay. Now uh, what exactly a swap chain is? The swap chain is basically, it's a queue of images. The idea here is that one image displays and you work on the another image at the back end, okay. So what you are doing is basically you are having basically multiple images or multiple surfaces, okay. So surface is basically a higher level, basically I would say the jargon, okay. And the surface provide basically images, and Vulkan work on images, okay. So like I mentioned, there are two type of resources, okay, buffers and images, okay. So if you are trying to render anything, okay, so images is something what where you have to render it, and where do you get these images? You get these images from the surfaces, and the surfaces are, they are very much specific to the operating system, and we are using basically glfw to create a Windows specific surface, okay. Now once I get these surfaces, like I mentioned, the swap chain is basically the, it's a queue of displayable images. So this is image 1, this is 2, this is 3, okay. And if you know about double and triple buffering, this is exactly the concept what is. Now if you understand double and triple buffering, this is exactly the same thing. So we have three images. So one image where GPU it's working upon, and the another image it's currently being transferred, whereas the third image is where the CPU is basically preparing it to render, all right. So now you can clearly see that each surface has basically certain format, and then it has basically present mode, okay. So we will see this present mode when we'll come later, but right now you don't have to worry about it. But all you need to worry about is basically a high level understanding how basically these uh, basically uh, the Vulkan application programming model works, all right. So now how you can actually get these swap chains, which are basically a queue of displayable images, this is how you get it, all right. uh, One thing maybe actually I'll like to highlight here is basically the present mode, okay. So don't worry about the API, but I think since actually I mentioned it, so it's important for us to look at. Now if you'll see basically there is a particular parameter which is called the present mode, and we send the present mode as vk present mode mail khr, okay. So in layman terms, what it's trying to do, it's basically it allows you basically a smooth animation and continuous rendering, okay. So this is specifically the triple buffering. That means the GPU always shows the latest completed frame buffer, okay. I mean, without any latency problems or tearing problems, okay. So this is basically we are indicating to use basically triple buffering here. Now so I would say that, I mean, swap chain is basically it's the heartbeat of your renderer. So what you are presently doing here is basically every time you wanted to render a particular image, whether it is 1, 2 or 3, you will acquire that image, okay. Once you that acquire that image, you want you are basically wanted to render on it, and once you render on it you wanted to present that. Okay, and this is basically a continuous cycle, okay, that keeps on basically working, or basically going on in a render loop. So I would say that, I mean, you are actually not rendering anything to the screen. What you are rendering is basically you are rendering everything to the swap chains, okay, and or more specifically you are rendering everything to the swap chain images. Now this is basically a new jargon, and now onwards actually you will see that I'll be continuously using this term called swap chain images. So anytime I'll use swap chain images, so don't be get confused. So these are just basically a queue of displayable images that we are getting from a particular window, okay, and these windows are basically operating system specific. All right, so now this is the another important concept that we are stepping into, and I would say this is one of the most powerful concepts of a Vulkan, which is basically the Vulkan memory management. Okay, now before actually I'll start dwelling into this resource setup. Okay, one thing that actually I like to clear every junior developer or basically the student, that in Vulkan there is nothing automatic. Okay, so you have to do everything by of your own. That means if you are working with images, buffers, you have to control the memory. Okay, now this is a different case in OpenGL, where the driver does basically a lot of memory management for you. Okay, so it basically smartly choose basically the heap that you are interested in, and it decided where your data is going to live. Okay, how the data is going to move, or how, I mean, basically quick the data can be accessed, but this is not a case in Vulkan. Okay, so I would say this is a reason why the Vulkan gives you performance, because uh, it helps you to directly manage your memory. Okay, so how it does, maybe actually I'll help you to understand more by covering the next topic. Okay, which is basically the memory model. So when you actually create a Vulkan instance, it actually exposes various type of uh, devices, right, the GPUs, and each DPU has basically a specific memory model, okay, that Vulkan is capable of exposing. Okay, so it basically exposes different type of memory. Okay, and not all memories are basically equal. So for example, how to help you explain, I mean, okay, in a layman term, since you are very new to it, this, I mean, I can say that Vulkan expose different type of memories. So you can have basically some memory which is completely GPU specific. Okay, we called it as basically device local memory. Now the property of this memory is that it is very fast, but your CPU cannot access it. All right, now then you have basically a second type of memory, we called it as host visible memory. The host is here is your basically CPU. Okay, and it indicates that this type of memory can be accessed by your CPU. Okay, however this is slower for your GPU. Okay, so this is how basically it exposes various type of memory, and you can use it to better control your memory management. Okay, now for performance you wanted to choose basically a specific type of memory that helps you to serve the purpose. For example, you have a vertex buffer. Okay, like a 3D mesh. Okay, 3D mesh of basically uh, some model. Okay, so let's call it, I mean, I have basically a Suzanne. Okay, it's an OBJ or basically 3ds file or basically an FBX file. Now this 3D mesh, it's not going to change, so I always wanted to basically store this mesh onto a GPU because it's not going to change. All right, so I would basically choose basically a device local memory, and I will just do the transfer once, and then I just need to just update its model view metrics to, I mean, get interacted with it, or basically change its position into the 3D world. However, I can have the same buffer, which is basically a vertex buffer, but this vertex buffer, it does not belong to a 3D mesh, but what it's belong to, it's belong to a point cloud. And here the point cloud, it's not static, the point cloud is basically dynamic. For example, I'm getting an input from a lidar. Okay, I'm creating an application for an autonomous vehicle. The autonomous vehicle is basically mounted with 2 or 3 lidars, so they get basically the data of the surroundings, and all the data is basically a 3D point cloud. So you wanted to visualize that. All right, now you are getting basically all those point clouds. I mean, it may be basically very dense. Okay, so it could be 500k, it could be million, or it could be even low. Okay, depending upon the kind of lidar that you are using. But how do you actually render this? So that means now you need basically uh, a set of memory. A set of memory, that means it may be an amalgamation of different type of memories. So you are basically having some memory which is CPU visible. Why CPU visible? Because the data, it's coming from some sensor. It first comes to your local memory, the CPU needs to see that. Okay, then this memory needs to transfer into the GPU, okay, which is a device local buffer. So we something called it as basically a staging buffer. So what staging buffer does, it's basically it copies your buffer, it copies your buffer from your local CPU to the GPU. Okay, so what you do is basically you first create a copy of your large memory, you copy the data here, and then you basically create a device local buffer, and you transfer into that. Okay, now there are, I mean, definitely 2 level of copies, but this is much faster. I mean, just trying to basically use one type of memory. All right, so this is basically one of the strategies how you can actually use basically your data to transfer from CPU to your GPU. So there are basically certain things that you should be I mean look at. I mean, when we talk about basically the resource setup, that means we are talking about the buffer management, and basically we are talking about the image management. Okay, so what is VK buffer? So VK buffer is just only raw memory. Okay, so just think of it like a container that comprises your vertices, or basically it's a container of your indexes, or maybe it's a container of your uniform data. Okay, like we did in SSBO. Okay, so it's basically a large memory, it's a raw memory where you just put your data into it, and you specify your data into a particular format. Okay, now whenever you actually specify a VK buffer, it does not have basically the actual memory. The actual memory comes from VK device memory. So you specify your VK buffer, and then you provide it to VK device memory. okay, where it actually creates your resource. So what it does is basically it first allocates the memory, and then it basically bind that memory to your data. Now the next thing that comes is basically the another type of resource, which is VK image. Now the VK image, they are not basically raw memory, but I would say that these are structured resources. Structured resources, that means they are formatted resources. So they are basically textures. Okay, this could be depth buffer, or it could be basically render target. So VK buffer, this is a linear data. So this is a linear data, whereas VK images, it's basically a structured data. Okay, so structured data means this is basically images or textures. Now one thing that actually I want you to pay attention is basically to a pitfall, because there, I mean, this is where actually I notice many people, they make mistake. Okay, one thing that you need to ensure is that when you work with memory for a GPU, you don't want it to allocate the memories again and again and again, for two reasons. First, allocation of memory, it's very expensive, whether it is allocation or whether you wanted to release that memory. So that is very expensive. So what you wanted to do is basically you wanted to basically allocate a large chunk and then sub allocate small chunks for your application. Okay, and we have basically you can do it manually, but we do have some tools like VMA, Vulkan memory allocator, that helps you to build your application without dwelling too much into the memory management. So some good people, they create this helper API for you that you can actually make use of it. So this is very important. So the takeaway is that avoid avoid continuous allocation. Instead, if you need a lot of allocations, okay, use basically a large allocation, then sub allocate the pieces that you wanted to them, and just reuse them. Okay, now we are stepping into one of the most powerful concept of a Vulkan, which is basically the graphics pipeline. Okay, more specifically, it's a pipeline. It could be a graphics pipeline, it could be a compute pipeline, it could be another pipeline. But what I am interested here is basically giving you an overview of pipeline through a graphics pipeline. Okay, so I think that would actually help you to understand things very clearly. Okay, now I would say that a pipeline is just not basically a piece of code, but I would say it's something which is, once you written, it's baked into the GPU. So that means the GPU, if you see on your screen, these are basically all the steps that you are actually doing for a graphics pipeline. Okay, for compute pipeline you don't have those many uh, basically configurations, but for graphics pipeline you have basically such configurations. Okay, and you have to do it, but that does not mean that when you are into a render loop you have to again execute these every time. So what you do is basically you write them once and you bake it into the GPU, and all GPU does it basically, it just look at your graphics pipeline state objects and it make use of it. And those pipeline state objects, they know the states, they know the shaders, they know the input assembly, rasterization, any setting related to blending, layouts or depth, Okay, it's capable of getting those information, and from those it can easily look at the descriptor set to basically look at the formats and use it in the render pass. Okay, so now let me help you understand the graphics pipeline. So like I mentioned, there could be a number of pipelines. Okay, so the basic object of the pipeline is basically VK pipeline. So VK pipeline, it's where it takes basically different states like shaders, input configuration, rasterization, blending, okay, anything like that. So this VK pipeline actually bakes everything together into a GPU object. So maybe actually let's look at this pipeline step by step. Okay, I'll just give you a flavor of uh, I mean how a pipeline is basically breakdown. Okay, so let's break down this conceptually. Okay, now the pipeline basically it includes of various stages. So these stages could be basically stager stage, input, assembly, viewport, and many others. So let's look at basically the stages. Shader stage. Now the shader stage is basically you specify your shaders. Okay, the shaders could be more than vertex and fragment shader, but if you are just doing basically a simple rendering of your meshes, all you need is basically a vertex and fragment shader. And you have to remember that here we are not sending the source code. What we are sending is basically the .spv file. Okay, and the .spv file for vertex and .spv file for the fragments itself. Okay, now the next step actually that we have is basically the input assembly. So input assembly, we wanted to tell the GPU how you are going to treat the vertices that we send, whether you wanted to treat the vertices. So for example, I send basically 3 vertices. Okay, v0, v1, v2. Okay, so this is counterclockwise. So how the GPU actually look at these 3 vertices, how it will basically assemble it, whether it needs to assemble these point as basically triangle, whether it's basically need to assemble these points as basically line. Okay, this line or basically a line loop like this, or it wanted to treat it as basically points, which is something like this. Okay, so vertex 1, vertex 2, vertex 3. Okay, now after this one actually we do have another stage, which is we called it as viewport and scissor. Okay, this is the similar stage that you had in OpenGL, so I'll not basically go into this one. Then you have basically moved to depth and stencil testing. Now this basically determines, for 3D applications, what is visible and what is basically hidden for you, and how you basically followed in your color blending. So all those rules are basically specified here. Okay, now finally we have basically a pipeline layout. Now the pipeline layout, it tells basically which resources. When I say resources, it means descriptor sets. Okay, so which descriptor sets are basically connected to the shaders. Why? The descriptor sets, they are basically the interface between your shaders and your resource, which is basically your buffer and images. And why is it an interface? Because your shaders need to understand the format in which the data is coming, right? So it needs basically some kind of hint that your vertex is basically it comprises of RGB A8, it comprises of your vertices, which is basically float 32. Okay, and it has basically three components into it. So all those kind of information are basically specified through the descriptor sets. So now let's basically uh, I think I have covered the descriptor sets. uh, so descriptor sets, so I'll just repeat it for you. So the descriptor sets is basically an interface between your shader and your resources. Okay, so this is basically your shader, and this is basically your resource. Okay, the resource could be a buffer or it could be an image. Okay, so this is basically a bridge. Okay, so this is the descriptor set, so this is the bridge between these. Okay, and descriptor sets, I'm repeating because it's an important topic. Okay, what you will see is that in Vulkan you are actually setting up a lot of descriptor sets. Okay, so it's very important to you understand, I mean, what exactly descriptors are. So they are basically the data binding, so the data binding on your CPU resources to your GPU shaders. Now the another concept is basically the pipeline cache. Okay, so the pipeline cache is basically uh, like the uh, how to explain you, so it's the cache of your pipeline. That means the pipeline object that you are creating, okay, it's basically cached. Okay, and basically it allows you to reuse pipeline state across various runs. Okay, so what it does, it basically it reduce the basically startup cost. Okay, if you are basically using Vulkan, one thing that you can do, you can store this pipeline state into a persistent object, and next time your application starts you don't need to recompile it again. Okay, so first time you run your pipeline configuration you have to compile this. Okay, but if you are not saving it into a persistent state, okay, that means next time you physically start your application it needs to recompile it. But once you recompile it, it basically stored into a pipeline state object. Okay, and that pipeline state object is into your memory and you can reuse it. But that pipeline state object you can also store while you are exiting your application into a binary format. Okay, so the next time your application start it can reuse it. Now one thing which is very important, that pipeline creating pipeline states, they are expensive. Okay, so it basically involves a lot of compiling and linking GPU resources. Okay, internally. So you want it to basically you don't want it to create the pipeline state objects frequently. Okay, so otherwise it will drop you the performance significantly. Okay, so what you wanted to do, the ideal way is basically you create the pipeline state objects only once. Okay, then you try to reuse them across your multiple or across your draw calls. And when you are basically into a render loop, okay, try to avoid any creation of your pipeline state object. Okay, so you should be designing in such a way that your pipelines, they are always created when you basically create your application. All right, Now the next thing is basically command buffers. Okay, so in Vulkan the commands are not executed immediately, so they are always recorded. Okay, and this is something what actually I show you in uh, the Vulkan execution model slide. Okay, so whenever you are basically using some commands, the commands that actually starts with vkcmd, 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 so all these are basically commands that you wanted to record into your command buffer. Okay, so these commands like vk bind pipeline, bk draw indexed. Okay, so here you are actually trying to draw something. Okay, so when you specify these are not immediately basically executed on the GPU, but these are basically recorded. Okay, so these are recorded into a command buffer. So you can see this is basically the start is happening, and this is where the command buffer recording ends. Okay, so the recording starts here and recording ends, and within this recording I have basically a render pass. Okay, we will look at this later, but in this render pass what I am doing basically I'm recording a set of commands. Okay, and all these set of commands they are basically stored into this command buffer object. Okay, so this is the same command buffer object. Okay, so if I'll help you to actually uh, understand this pseudo code. Okay, so the very first thing that actually we will do is basically we will start with vk begin command buffer. Now this is where the marking of your recording or basically it marks the beginning of your recording, right? So then the next thing that we do is basically we begins the render pass. Okay, so uh, what a render pass does, I mean in a layman term I would say that I mean it defines where we are rendering. Okay, so it typically points to a frame buffer from a swap chain. Okay, so it tells where exactly we are rendering. So frame buffer image index is basically, so we have a number of images right in a swap chain, so we are telling that you go and render into basically image 0. Okay, and in a render loop this is keep on incrementing to 1 to 0 1 2 then 0 1 2. Okay, repeatedly. Okay, the next thing that we actually do in the recording is first we created a pipeline state object. Okay, so we bind that pipeline here. Okay, and then we follow with the descriptor sets. So these descriptor sets basically it connects our shaders which we have specified in our pipeline. Okay, to the textures and the buffer resources. The next thing that we will do is basically we will bind the buffer. Okay, so in binding the buffer what we are doing basically we have basically our vertex buffer and index buffer which contains the actual geometry and the layout. Okay, not the layout but the index order of the vertices. Okay, so this is what we specify next. Now once we have done this there is also basically we define the viewport and scissor. Okay, so this particular rendering, which part of the viewport it basically render to, and what is basically the scissor parameters of this of the uh, of the rendering. Okay, in other words we are controlling how the rendering region is basically drawn. Finally we issue basically a draw command. Okay, which is basically this command. What it does is basically it draws the index buffer. So that means you have a buffer which contains indexes. Okay, and it draws the image on the frame buffer target that actually I have specified in my render pass. Okay, so one thing that you still need to remember is that currently it's just still recording, there is no execution. Okay, the execution would happen when we submit this command into a particular queue, and that queue is basically being then processed by uh, the GPU. Okay, the next thing that is which is very important, that currently we are recording a command buffer, and like I mentioned that the command buffers, they can be recorded into different threads. So what command pool does, it's basically it provides your command buffers from this pool, and this is very helpful when you are basically making use of multiple threads. So each thread has basically its own command pool. Okay, so it does not need to synchronize the command buffers. Okay, so each thread basically make use of uh, its own pool, so there is no lock contentions here. So the next point is basically the reuse pattern. So by reuse pattern, I mean that, I mean you are interested in recording your command buffers one, and once they are recorded, you are basically wanted to reuse them. So that does not mean that you need to recompile these 10-15 statements every time. So once you have recorded, everything is basically stored into this command buffer into a binary format. Okay, as an, or basically as an object. Okay, it is stored in the form of the object. Okay, so you don't need to worry about that. Okay, now the last important point is that all these Vulkan command buffers that we have actually recorded, so they don't get executed unless we go and submit this command buffer. So this is the command buffer. So this command buffer we have to submit into the queue. Which queue? In the beginning, when we create the devices, we have also basically query the queues that we are interested in. So this command buffer will be get submitted to that, and once we submit it, it will basically execute it upfront on the GPU. Yeah, sorry, I mean the lecture is getting a little bit long, but I think from the programming point of view, I think this is important, and this lecture would help you in future for your interviews. So but this is all the backbone that we have. Okay, now this is basically the very last stage that we have for our Vulkan programming model. Okay, now I would say that this is now we are entering one of the most critical and challenging part of our Vulkan, because it comprises of queue management, submission, and synchronization. And synchronization is where a lot of problem happens. Okay, so I want your full attention here, because this is where most of the application they they got bugs. Okay, so most of the bugs that happens in the real world application is in this stage. Okay, now one thing that you need to understand before I start, one thing that you need to understand is the CPU and GPU, they do not work together. Okay, the CPU working at its own pace, the GPU is working at its own pace, the CQ has basically a fewer threads, okay, fewer codes, fewer cores, whereas the GPU, it has basically a lot of cores. Okay, cores in thousands. Okay, so they work asynchronously. Okay, now that means that the CPU and GPU, they have to handshake. Okay, shake hand. Okay, before they actually do any job to ensure that everything it's working in order and as expected. That means your GPU might already be preparing next frame while your GPU is still working on the previous frame. So the CPU has to stop until the GPU is not basically finished its job. So because of this, Vulkan does not automatically manages the order or any safety for you. So you are basically 100% responsible for your own synchronization. Okay. So now if you wanted to control this behavior, the Vulkan provide basically a lot of synchronization mechanisms. So these synchronization mechanisms are basically Vulkan semaphore, fences, events, and pipeline barriers. Okay, so all these are basically synchronization mechanisms. Okay, so I will just give you a taste of these at a higher level. So the very first one is basically the VK semaphore. I mean, it's a semaphore. What it does is basically it use for GPU to GPU synchronization. If you have two jobs on the GPU and if you wanted to synchronize them, okay, this is where actually you make use of semaphore. Okay, we make use of semaphore highly in our swap chain. So how we use it? So basically we typically use between the queue submissions. So for example, if you wanted to ensure that the rendering does not start until the swap chain image is already ready. That means you wanted to render your job onto image, right? But that image must be available before you start writing on it. Okay, and this is where actually you make use of semaphores to ensure that before you start rendering, the image must be available, and if it is not available, you go into a wait state. All right. The next thing is basically the VK fence. The VK fence, they are used basically a CPU and GPU synchronization. Okay, so I would say CPU and GPU. This is GPU to GPU synchronization. Okay, so the VK fence, which is basically used for CPU to GPU synchronization, that means it allows your application to wait until the GPU has finished its work. Okay, when I say application, your application is running into your CPU, so it will allow the CPU to basically query whether a job is basically finished onto the GPU. If it is not finished, then it will just keep waiting, or maybe it can do basically some other task in parallel. All right. Now the next we have basically VK events. Now VK events are basically fine grained synchronization. So if you have basically multiple commands in your command buffers and you wanted to basically synchronize your command buffers, so this is where the Vulkan events are basically used. So you are basically doing a fine grain synchronization within a single view. Okay, now one thing which is important is basically this is within a single queue. Okay, not across multiple queues. Okay, so the event actually manages synchronization of your command buffers within a single queue. So basically it allows you to control the ordering of your command buffers. Okay, the next one is basically the pipeline barrier. Okay, I would say that this is one of the most powerful and very commonly used mechanism. So let's suppose you're writing basically some statements of Vulkan. Okay, so which defines basically certain operations. So when you actually implement a Vulkan barrier, what it does is basically it controls the execution order and the memory visibility. So what it does ensure is that it ensures that these certain statements does not execute until a certain operation is basically completed. Okay, so Later, actually, I will give you some examples of pipeline barriers into my examples. But right now, I think you just try to understand basically these. But most of them, which are particularly used, are basically VK semaphore and fence. So at least if you are going for an interview, you just remember all the names of these, but most importantly the synchronization mechanisms which are used, which are very common, is VK semaphore for synchronization of your swap chains and VK fences, okay, for your CPU GPU synchronization. All right, so this is basically where everything comes together, and I would say that this is basically the final piece. Okay, now this final piece, it puts everything together, and we are doing basically a per frame rendering. So this is basically, this code is basically per frame rendering group, or basically it's a rendering group of one frame. Okay, now this rendering loop, it basically drives everything for your graphics application. Okay, now it would also not be wrong to basically called it as basically a heartbeat of your entire application or game engine, because it's happening regularly, okay, for each frame buffer. Now if you wanted to understand this pseudocode, I mean it's basically very simple. Okay, so mm, so maybe actually let's look at this one. So the very first thing is that you will find basically a while loop. So this while loop is basically, it's continuously running, and it's ensure that until the window is not closed, it will basically keep on running. The very first thing it does is basically it pulls the event, it looks for mouse keyboard events and basically process those. The next thing it does, it's basically it looks for uh, the images. Okay, and right now actually if you'll see that we are looking at basically some code which is waiting for a fence. Now what this waiting for a fence it's doing, well, we have some frame buffer which is available with our GPU, and the GPU has not finished working on it, or maybe it has finished working on it, but we do not know. So we wanted to wait for the GPU to finish that. But how to check whether it is finished? Using the fences. Just now I actually mentioned you that the fences, it helps you to synchronize your CPU and GPU operation, and this is one of the very good example. So once you have basically the signal available, that what you do, it's basically you get basically the available image on which you wanted to write. Okay, and once that image is available to you, what you do, it's basically you will provide your command buffer. Okay, so your command buffer, it's going here. Okay, so I do have basically a lot of command buffers. Okay, I do have basically, like I have basically multiple uh, triple buffering like swap chain images. Okay, similarly I do have basically command buffer for each image. Okay, so when I work on this command buffer, I just wanted to submit this command buffer. Okay, and when it is working on the GPU, I wanted to use another command buffer. Okay, so like 12012, so which is the index of your images. So these are your swap chain images. Okay, similarly I do have command buffers. So for each swap chain, not for each swap chain, but for each frame, I do have basically different set of command buffers, because these command buffers, they are getting executed on GPU, right? And I don't want it to override them. So once I given this, I wanted to work on basically a new set of command buffer. Now that is what exactly it means by command cmd in bracket index. So I have basically a particular index on which actually I'm working on. Now finally, once I basically submit this thing, okay, it will get executed, and then I wanted to basically present the rendered image onto a current basically, or the interested swap chain. Okay, now every time I basically go through this loop, what I do, it's basically what is max frame in flight. Max frame in flight, it indicates that I'm using 3 frames, okay, or 3 images. It's a triple buffering. So what it does, it basically, it will produce the output as 0 1 2 0 1 2 0 1 2 every time. Okay, so it will indicate which is your current and which is your next frame buffer index. All right, and using this frame buffer, this using this index, you can point to current image that you are working on, or the next image that you are working on. Similarly, it goes for the command buffers. All right, now this is basically the entire Vulkan initialization that actually I mentioned you. It's basically a cheat sheet. Okay, you can look into this. I've already explained to you. Now I think we are almost moving towards the end of some of our slides. So we have 5 or 6 slides. Okay, so um, now this is basically the third part of your presentation in today's lecture. So now in this slide, actually we are trying to basically answer one of the important questions, that why we are learning Vulkan. Okay, so like I mentioned before, that Vulkan is just not an API. It basically provides you the direct control of your hardware. Okay, you use it for tuning the performance, you use it for basically building application that are truly predictable. Okay, and it's basically also allows you for a scalable development, where you are basically creating cross platform application. And one of the most important aspect of using Vulkan as an API, it is basically truly scalable in terms of multi-threaded applications. So you can actually do multi-threading, which was not possible earlier. Now let's look at basically the key benefits in practice. The very first one, I think I have already covered it, so maybe I don't need to go into this one, but you just go through the slides. I think this is something I have already covered into the previous slide, so you don't my previous lecture, so you don't need to go into this. Okay, if there is anything specific I wanted to cover in this topic, yeah, maybe actually I'll cover this topic for you. Okay, which is the graphics and compute. Okay, so Vulkan is basically a single API. You don't need to use another API for your web applications, for your mobile application, embedded applications, or your desktop applications. So you use only one API. Okay, and the Vulkan actually comes along with graphics and compute capability. So you are just not doing graphics application, but if you do want it to do general purpose GPU, that is also possible through the compute. Okay, we call it as GPU. Okay, now the next thing is multi-core scalability. Now for your multi-core scalability, I would say that it's very critical for your modern GPU hardware. And with Vulkan, it basically allows your command buffers to record in parallel across multiple CPU threads. So that means it ensures that your GPU is always fully utilized. You don't want it to ensure that your GPU is underutilized. So what you try to do is basically you try to record multiple command buffers into multiple threads and submit those into queues. Since the command buffers, they are basically from different command pools, you don't need to synchronize I mean, you may need to synchronize them, but you don't need to uh, I mean, look for any race kind of conditions, right? So you can fully process them in parallel in your on your GPU. And I would say that this is where your system, your design system becomes scalable with your hardware. Okay, so this is the important 2 points that actually I like to cover for you. Now this slide, actually I would say that it connects everything that you have learned so far from your application point of view or game engine architecture point of view. And I would say that here the Vulkan, actually it truly becomes meaningful. Okay, now a modern game application or basically a modern application, it's just not basically a single system, right? Now it comes along with a number of components, okay, a number of basically modules. It could be a physics module, it could be an audio module, input, scripting, resource management, or basically your scene management, anything like that. Now, so one important question is where exactly the Vulkan sits into it. Well, you don't want it to use directly Vulkan into your physics, audio, input, scripting, but you want it to create a separate module where everything which is related to Vulkan or related to graphics or compute sit together. Okay, and maybe I can call that module as a rendering engine because I'm creating a graphics application, or if you are doing some compute application, you can call it as a compute engine. But the idea is that you wanted to keep all your Vulkan commands here. It should not be bloating, it should not be basically going out of the into other modules. Okay, and you can better abstract it. And why Vulkan? Maybe actually you wanted to, I mean, scale it to DirectX or Metal as well. Okay, if you wanted to provide basically a direct support or utilize the GPU which are very specifically made for that. Okay, so this is where the abstraction of your engine comes. Okay, so it can, so your rendering engine, which is basically this part, okay, it may support basically Vulkan. Okay, it may support more APIs. The idea is that the more APIs you support it, I mean, the more complex handling you have to done. But using Vulkan, it already make it basically cross platform, across Unix, across other operating system. Okay, Ubuntu, Mac, even embedded systems like Android. All right. So I would say that the Vulkan is actually, it works as a direct interface between your rendering engine and your GPU hardware. Okay, the another concept which is important when you actually making use of Vulkan, it's basically the modular architecture. So I would say that, I mean, in professional applications, whether it's basically game engine or your application, a specific application, the systems are designed to be decoupled and reusable. Okay, in my next lecture I will actually give you a very simple example of decoupling and reusability through Windows. Okay, so maybe actually I'll show it in the next slide. Okay, but this is how you have to basically approach a modular design. Now this is basically a very high level overview of the very first application that we are going to do in our next lecture. Okay, but one thing that actually I wanted to I mean show here is that when you start implementing your graphics or any compute project or maybe even any other basically project, it's very important to basically segregate the things. Okay, so that you don't have basically code which are basically uh, spilling over. By spilling over, I mean to say that in your previous application and projects, you have used GLFW, right? You have used GLFW not only for surfacing but also for key events, right? Key events, mouse events, and any other basically joystick. But you don't want it to basically use your GLFW everywhere, okay? But the best part is basically you want it to keep restricted into a particular module, okay? And I will say that module, or basically uh, module or a component, okay? These are basically high level uh, blocks, okay? So the idea is that you wanted to keep your GLFW into maybe a class like window, okay, where it handles all the Windows application, and where it also actually handles your basically high level events, okay? Or maybe you can have basically an event class, okay? But this is where you have to separate your engine from your application itself. So your application should be very separate from your engine. So this is basically a high level overview of the first program that we are going to do in our next lecture, okay? So what we are going to start is basically we are going to start with a real project that we are building, and it's just not a simple example. So what we will try to do is we will start basically programming an actual application engine or a game engine structure, okay? So what uh, what important for us is basically instead of basically writing small disconnected programs, we will develop basically a complete modular application step by step, or basically a game engine step by step. So we need basically a very clean directory structure. So we need basically an engine which is basically a reusable code, and we want it to make it reusable through a static library or through a dynamic library. Our game or our test application would be separate, okay? And I'm putting a folder called sandbox. So in sandbox I do have 10 applications that is making use of my engine, okay? It may be creating 10 games, or it may be creating 10 different applications, and my engine, it's working like a static library, and it's a framework, okay? The engine that actually I wanted to develop as a framework, okay? So it's a complete command line based application. So you can basically interact with it, okay? You can use with it, and you can also basically use this application to create an editor out of it, okay? So my engine, it does not contain any editor specific things. It's a complete command line based program. It does not have basically anything specific to a particular operating system, okay? So I just wanted to use this engine into my sandbox, and my sandbox could be a game application, my sandbox could be a specific dedicated application, okay, that I wanted to. Now the another important concept is we will create our examples in incremental growth. So I will start with a very simple main program, okay? The very first thing that actually we will do is basically we will create a Vulkan instance. We will talk to the GPU, okay? Once we talk to the GPU, we'll print it in a command line fashion, okay? All the capabilities, we will choose the devices, we will query the queues that we are interested in. The next step that we will do is basically we will create a window out of it. So we will integrate our GLFW, we will implement this window class, okay? So all this would be basically in a step by step way, okay? That's what actually I mean by the incremental growth. All right, now yeah, I think more or less I think this is something what actually I wanted to cover. Maybe let's look at the next slide what it comes with. Okay, so these are basically some of the key terms that actually I have added for you. So the idea is that you should be at least remember these APIs, okay, and it should be on your tips, okay, and you should be knowing what exactly it means. Okay, I have already covered in this lecture, so it's a kind of cheat sheet for you. Okay, so you should be able to know, I mean, what it does. All right, next. So the next thing that you need to do is basically you need to install Vulkan. Okay, so in the next lecture I would start basically a real-time programming for our Vulkan application. So for this one you need to do basically Vulkan installation. Now I have basically two slides for you. So maybe you wanted to go for a manual Vulkan installation. Okay, so for the manual Vulkan installation you have to basically follow these steps. Okay, and once you follow these steps you can actually install the Vulkan. Okay, the another one that I have and mostly I use is basically in my repository I do have basically some scripts that I constantly use on different operating systems. So if you are comfortable, okay, what you can do is basically you can, since we are, I mean, using Windows most of the time, you can just go launch your command line. Okay, PowerShell, you have to use PowerShell and execute with the admin privileges, and you have to basically run this install window ps, okay, batch script, and once you've done it basically it will automatically install the Vulkan for you. All right, now these are basically the key takeaways from today's lecture. So I think uh, it builds you the Vulkan vocabulary, okay, and this will help you in both your interviews and real development. Okay, so I would say that in Vulkan every concept is basically represented as an object. Okay, understanding these names clearly, okay, will make everything much easier for you. Okay, so for example you should be knowing what exactly vk instance is, what exactly it does. So for example vk instance is an entry point to Vulkan. Okay, vk physical device represents the actual device, vk device is basically the logical device to that hardware. Okay, so all sort of things are basically very important for you from an interview point of view. And perhaps uh, usually at your level where you are basically a junior developer or student, I think not many things actually comes out of these first three lectures that I have covered for you. Okay, so if you are going for an interview, watch these first three lectures, they are basically all fundamental theories. Okay, just take the notes, record it down, and remember those, it will help you to clear those. Now the rest of the lectures that we are covering, it would be all incremental, so we will try to create basically a real application with Vulkan. So the very first approach would be I will be creating a monolithic code that will give you a simple minimal hello world kind of application. But since we are actually talking in terms of application and game engines, we want our code to be scalable. Okay, and this is where we will follow the modular approach, and we will start segregating into different classes, and we will create our application engine or a game engine library. Okay, now uh, yeah, I think you can actually go through, I mean, rest of these points. I think they are pretty much forward, I don't need to repeat these, but these are self-explanatory. Now if you need any if you have any queries, any questions, I mean, just use the channel that we have, or you feel comfortable, just ping me directly your queries. Okay, I'll try to help them. Okay, I mean, and if it is useful for others, I'll actually explain the details in the thread itself. All right, so I think with this one, I think we are almost at the end of our lecture. So I mean, this is one of my take is with Vulkan, that it does not actually hide any complexity, but if you are actually learning Vulkan, it actually teaches you what exactly going in the GPU. Okay, so at the end of the day, I would also say that it does not simplify the things for you, but it actually exposes how the internal GPU is working. Okay, now this is very important. So because you are just not relying on hidden abstractions like older APIs that provides you. Now you are basically thinking like a system engineer, because you know how the data flows, how the command buffer executes, how you have to record them, how you have to perform the optimization, okay, how to deal with performance. Okay, you are working with CPU and GPU, so you need to understand basically synchronization uh, mechanism. Okay, so now the next step, it's very important. So we will finally move from theory to practice. So in the next lecture, we will set up the complete development environment. So I have, in my last two slides, I have already provided you the Vulkan SDK, so that you can actually install and you can configure your system. Okay, and just verify whether the Vulkan is basically properly installed. Okay, you should also be setting up the tool chain. Okay, that is basically you should be having CMake and the modern C++. Okay, and I think this is quite good enough for us to start the foundation of Vulkan programming. Okay, now yeah, I think this is all I have for you in this lecture. So yeah, it was basically a long lecture, but yeah, I think this is important from a high level programming model point of view. So we understood the execution model, and we have also seen the Vulkan programming model. So if you have watched this entire lecture, I think this is all we are going to do in next few lectures in practical. Okay, but this is a high level taste of what the Vulkan programming would look like. All right, now with this one, actually I'm signing off this lecture, and I'll meet you in the next lecture. Thank you very much.